Sorry about that. Any questions? All right, and we last left off. We had just done the RC circuit, the RC AC circuit. It's the RC series AC circuit. So let's take a look at the RC parallel AC circuit. So there'll be a parallel, I'll have a resistor, a capacitor, a parallel AC circuit, so we'll draw the AC power supply, resistor, and I'll have a capacitor. So what is, given our usual, I guess, current, charge, and, oh, those are the two main ones. Let's rewind. Given charge and voltage, what's going to be the same for, I think I'm just supposed to begin. Given current and voltage, that's what I should have said if I didn't. What is going to be the same for objects in parallel? Will objects in parallel have the same voltage or have the same current? Yes, voltage. Because if they're in parallel, I've got a junction. If I want to get from one to the other, I have to pass by a junction, and if I've got a junction, current won't be the same. Unless it's a very special case. So, when I do my phasor diagram, since voltage is going to be the same, that's probably the best phasor with which to start. And again, you can put it anywhere, but I generally put it up in the third quadrant or up in the first quadrant. Now, I'm going to have in a phasor diagram, I'm going to have a phasor for the current and voltage for each of the components over there. So I should have 6 phasors. But I know that my voltage phasor for the resistor is the same voltage phasor for the capacitor, which is the same voltage phasor for the power supply. And for this, I can also just write epsilon for the EMF. So now we get into drawing the current phasors. So between the resistor and the capacitor, which one has a current phasor that is in phase? It's the stuff that was written over here on Tuesday. This is when Eli the Iceman pops in. It's the one not mentioned.
Good morning.
Good morning. See, at least doesn't even know the question. He's going to give the answer right now.
The resistor, E and I are in phase?
Yes.
That's exactly what I was going to say.
I know. She just cut you off. So because for the resistor, voltage and current phasors are in phase. In other words, my current phasor for the resistor is going to be along that same line. And as typical, the second one I draw is usually shorter, this is not necessarily indicating that it's a smaller number. It all depends on the units you use. So I'm going to label that I sub R. And now let's do. So for the capacitor, it's not in phase, so the current phasor is either 90 degrees ahead of it or 90 degrees behind it. And when I say ahead or behind, again, these phasors are going counterclockwise, as is traditional math. So for a capacitor, which comes first, the voltage or the current?
Current.
Why? Is that just a blind guess?
Cause isn't that what Eli the Iceman was?
Yeah.
Ice and like current before.
Yep. And that's ice. For the capacitor, current would come first. So the current. Now I know that whatever current is flowing out of the power supply, so if I imagine a So if I imagine current flowing out this way, it's going to split across those two. So the current coming out of the power supply has to be the sum of the currents flowing across the capacitor and the resistor, same with DC circuits. Except now I'm adding phasors and just instead of adding straight up numbers. So this would be the current from the power supply. And there we have all 6 phasors. Just 3 of them happen to overlap completely. Let's take it that next step and figure out what the impedance is. That is supposed to be a 90-degree angle there. That's supposed to be 90 degrees. So mathematically, I'm basically adding IC and IR to get IPS. That's a right triangle there. That's a right angle. Right angle. It's a rectangle. So I know that IR squared plus IC squared is equal to I power supply squared. Just physically. Let's go back to Ohm's law. I know that the voltage across the resistor, and again, for whatever reason, they typically don't put the delta in front of it. We're talking about voltage for in AC. This is equal to the current across the resistor times the resistance. And then for the other two, the voltage across the capacitor is equal to the current across the capacitor times the capacitive reactance, and the voltage across an inductor is equal to the current across the inductor times the inductive reactance. And then X sub C is 1 over omega C. X sub L is equal to omega L. So this stuff that I've written here is going to be true regardless of the circuit. I guess the stuff below the line is specific to this problem. So the current from the resistor is equal to the voltage from the resistor divided by the resistance squared plus the voltage from the capacitor over the capacitive reactance squared is equal to, well, when we're dealing with power supply, the Ohm's law variation of it is that the voltage from the power supply is equal to the current out of the power supply times the impedance. So this will be VES over Z. I know all the voltages are the same, they're in parallel. Emily said so. All the voltages are the same, and so I can just factor and divide it out. And so what I'm left with is 1 over R squared plus 1 over X sub C squared is 1 over Z squared. So my impedance for the circuit is 1 over the square root of 1 over R squared plus 1 over X sub C squared. And we can take it one step further. 1 over square root, 1 over R squared plus omega C. That would be the formula for this impedance. Questions?
Why did we get all those ones?
Why did we get all those what?
All the ones.
These ones?
Yeah.
Oh, okay. Taking the next step from here, all of the voltages are the same because in the circuit it's in parallel, and so the potential difference across from there to there is the same regardless of the path I take. So all the V's are the same, so I have V squared times 1 over R squared plus V squared times 1 over X sub C squared plus equals V squared over times 1 over Z squared. You accept that?
Yeah.
I can then divide everything by V squared and they go away.
Okay.
And now I'm left with this.
Okay. Works for me.
All right, let's do it with numbers. Seems like we started something with numbers yesterday, but we'll do numbers for this one. You thought what?
I thought you were gonna erase it.
No, no, not yet. All right, so we'll assume 60 hertz. And the RMS value of the voltage is 120 volts. My resistance is just add numbers here. Here we go. Resistance will make 15 ohms. And my capacitance will make 200 microfarads. And what I want to know is at, let's see, let me pick a reasonable time. And I want to know what the current across the resistor, the current across the capacitor, the current out of the power supply, and voltage across the resistor, voltage across the capacitor, voltage out across the power supply, at time is equal to .02 seconds. All right, so I'm trying to find, I need equations. Because all I've really messed with up till here, yeah, I've got equations sort of built into the arrows, but all of this stuff are dealing with amplitudes. These are all capital letters here, so I need to somehow get to the lowercase specific values. Now, I did not give enough information in order to know what the phase shift of the voltages are, so let's just go ahead and create a phase shift, and we'll say that the phase shift for the voltages is 5/6. We are dealing with radians here. In terms of degrees, 5/6 is what? How many degrees is this? And apparently I'm just talking
20s. No. 30.
30 degrees,
Thank you.
which is roughly how I have it drawn at that moment right there, ish. All right, so first we'll just put up some generic stuff. I know that epsilon is equal to big epsilon, or epsilons of, what I did subscript M before
Yeah.
for Maxwell. Cosine of omega t plus phi. Well, that would be the voltage for all of them. But we can, well, we know what that is because that's given to you. We just need to figure out epsilons of M and omega. Well, epsilons of M is the amplitude of my voltage. I know what the RMS value is. What is the relationship between the RMS value and the amplitude?
The relationship between them is that it would be, we have to square it, unit, root it, and that is how
And without,
how they're equal.
yeah, agreed. This is not complete, by the way.
Oh, no.
Well, in theory, I can make it come back. Yes, and with calculus, we can derive that. However, there is a shortcut. There's a very simple factor.
E equals E RMS, sorry, what am I saying? Sigma equals sigma,
Epsilon.
epsilon equals epsilon RMS square root 2.
Yes, square root 2.
I always want to call this sigma.
All right, and I gave you the RMS value, 120 volts. That this is U.S., Canada, Mexico standard. And I just saw the picture yesterday. Most of the world is on 50 hertz. Or sorry, not necessarily 120 volts. Anyway, so we end up with 120 times the square root of 2, and we end up with about 377. No, definitely in the ballpark there. 160 something.
169.71.
Units.
Volts.
All right, so we now know that value. Omega. And US, Canada, Mexico are on 60 hertz. Most of the world is on 50 hertz. I don't know why they chose those standards.
The period times 60, no wait, 2 pi times 60 hertz?
Period times 60 hertz would get you 1.
Oh.
This is the relationship, that's 60 hertz right there, because I have units of hertz and not radians per second. This is the regular frequency.
2 pi times the frequency.
Yes, omega equals 2 pi times the frequency. So this is 2 pi times 60 hertz. If you, well, I'm gonna throw some extra units in here just to show a subtle difference between these things. It's 2 pi radians per cycle. If you think about something spinning around in a circle, it's 2 pi radians for the circle times 60 cycles per hertz, per second. The cycles will cancel out, and you're left with radians per second. And this is the one that's 376.99?
Yes.
Yeah.